This video looks at formula for straight lines in compact form. So the first two videos have introduced the concepts of straight lines, but written formula in terms of real things. So I've used words like apples or euros or time. In general, it's necessary to use more abstract notation for straight lines, because this allows us to give generic interpretations or analysis, or indeed use algorithms and computer software. So this video is going to show how we can go from the specific, i.e. words like apples, to more generic notation. So here's the background that we derived in the previous video. We said if you have a horizontal coordinate, a vertical coordinate, you can see what the gradient is, and you can see what the intercept is with the vertical axis, then the formula for a straight line is given here, that the vertical coordinate is given by the gradient times the horizontal coordinate plus the intercept. But I hope you'll agree with me, having to write vertical coordinate every time, that's a bit tedious. Having to write horizontal coordinate, that's quite lengthy as well. Intercept, that's not too bad, but it's still long. And gradient. We want to understand these concepts, but not have to write such long words. So, up to now, we've used real variables for representing the vertical and horizontal coordinates. So we've done things like plot the total cost of apples versus the number of apples, or the cost in pounds of euros versus the number of euros obtained. Or we've looked at the energy expended versus the number of circuits performed. So you'll see real variables that represent real things. But in general, we want to write our formula much more compactly. We don't want to have to use such long words. So we're going to use the same examples as in the first two videos and show how we can actually make the formula more compact and therefore easier to deal with. We'll start then with the cost of apples example. A shopkeeper charges 35p per apple plus 10p for a bag to put them in. Use a graph to show the cost of up to 20 apples. Now we did that in the previous video, and here is the formula that we came up with. That the total cost in pence is the number of apples times 35 plus 10. So yes, that's a neat formula, but it's quite lengthy to write. Total cost in pence, 4 words, number of apples, 3 words, and so on. So what are we going to do? We're going to simplify this. I'm now going to represent the total cost in pence by a single variable. I'm just going to call it p. So wherever you see the word p, you just do a translation in your head and you say, oh, p just represents the total cost in pence. I'm going to represent the number of apples with n. So wherever you see n, you just say, all that means is how many apples have I got. N's a lot quicker to write. Now, if I make these two substitutions into my original formula, this is what I get left with. P equals n times 35 plus 10. And I hope you'll agree that this formula is a lot more compact than one we had before. And therefore it's quicker to write, and in the long term, a lot easier to work with. Now, here was the original graph. And you'll see in the original graph, we had a number of apples down here. We had cost in pence up here. So what change are we going to make? Very simple change. If you look at this graph here, you'll see now we've got n written down on the horizontal axis and p written on the vertical axis. Of course, if you want to, when you're plotting a graph, you can actually write what n represents and what p represents. Example 2. Jenny earns £5 per hour but pays £2.60 in bus fares. Represent her daily profit as a formula which uses the total number of hours she works. And you remember from the previous video, this is what we got. The total daily profit is given by the number of hours she works times 5 minus 2.6. So again, you see quite a lengthy formula given you've got all these words in it. So what we can do is we can represent the total profit with a variable p. So instead of writing total profit, I'm just going to write p. We can represent the number of hours by a single variable, and now I'm just going to represent those by a variable h. Now if I make those two substitutions, the formula above reduces to this. P equals h times 5 minus 2.6. And again you'll see it's a lot more compact and therefore a lot easier to work with. Example 3. So here the tourist can buy 1.2 euros per pound, but also must pay a £3 commission per transaction. And we derived the formula was the total number of euros they can buy is the number of pounds minus 3 times 1.2. So again, we can simplify this formula. We can represent the total euros they've bought with a variable e. We can represent the number of pounds they've spent with a variable p. So if I substitute those two in, this is what I get. I get e equals p minus 3 times 1.2. A lot more compact. Now I can rearrange that if I want by multiplying out the bracket, and then I get p times 1.2 minus 3.6. So here's a problem now. Sketch the graphs which represent the following formula, and you'll see we've already put these in compact form. So what it's checking is, do you remember the meaning of the variables in the different positions? So what you'll remember is that the bit at the end, the plus bit, tells you the intercept with the vertical axis. Okay, so what I'm going to have to do before I start is put some numbers in. So let's start with an arbitrary number. Let's say minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, and so on. So this can be y, and the horizontal axis we'll call x. And what should we do here? We can start with minus 3 again, minus 2, minus 1, 0, 1, 2, 3, 4, 5, 6. Okay? So we've got some axes, and what we can do now is we can take this first one, y equals 2x plus 2, and say what information is in there. Well, we're told that the intercept with the vertical axis is plus 2. Now the vertical axis is where x equals 0. That's this one here. And if I just mark the horizontal axis as well so you can see it. So all I need to do is find the plus 2. It goes through there. Now the other thing we've got is the slope is 2. So it goes up 2 in the vertical axis for every 1 in the horizontal axis. So therefore I can mark some points like this. And having got those points, I can draw my line. What about the next one? Y equals 0.5x minus 1. So again, you see the intercept with the vertical axis is at minus 1. So we mark that there. We see the gradient is 0.5. So for every 1 along, it goes up by a half. Or it's easier to say for every 2 along, it goes up by 1. So I can mark, again, some points like this. And there is my straight line. And if I do the last example in black, you'll see I've got y equals minus x plus 4. You'll see the intercept is at plus 4. We mark it there. And you'll notice the gradient is minus 1. So for every 1 along, it goes down by 1. So I can mark the points like that, and there's my line. And hopefully you can see how easy it is to go from this generic notation, okay, to the actual lines. So here's doing it backwards. Find the formula for the following lines. So I'll begin with the red one. And remember, what we're looking for is 2 pieces of information. If I write it here, we're looking for the intercept, and we're looking for the gradient. And the generic equation is y equals gradient times x plus intercept. Okay, so it's very simple. If I want to get the formula for the following lines, I just need the gradient and the intercept. So again, I'm going to mark the vertical axis, that's the one which goes to x equals 0 here, with a big black line, so we don't get confused as to which line we're working with. And so with the red one, you see the intercept is here, it's at 2. Okay, if I try to work out the gradient, you'll see it's gone up by 6. Sorry, it's gone up by 6, mark it carefully, and it's gone along by 2. So the gradient, 6 over 2, is, sorry, I've got to be careful there, and this is what happens. It's actually gone up by 4. Now there I've demonstrated a very simple mistake that you could make if you're not careful. So be very careful, mark these double arrows and say how far has it actually gone up. So from 2 to 6 it's gone up by 4, it's gone along by 2, and so the gradient is 2. So here we've got y equals 2x plus 2. So there's the formula, okay, for the red line. What about the blue line? So if I go to the blue line, you see the intercept is down here, it's at -4. And again, we need to work out the gradient. So if I do this where it's simplest, I can see here I've gone up by, now how much have I gone up by? If I mark that, you'll see it's gone up by 1, 2, 3, 4, 5, 6. So it's gone up by 6. It's gone along by 2. So the gradient is 3. So for this line, I've got y equals 3x minus 4, because the intercept was -4. And finally, we've got this magenta one, which I'll use black for. You can see the intercept is at +4. And if I work out the movement, you can see I've gone down by 3 and along by 2. So the gradient is -3/2. So what I've got is y equals -3/2 into x plus 4. So hopefully that's straightforward. You can see all we're doing is we're reading off the gradient, we're reading off the intercept, and we can write the formula straight down. So we've introduced the use of simple variables to represent the data in straight line graphs, and shown that these can be represented by simple formula of this type: y equals mx plus c, where y represents the data on the vertical axis, x represents the data on the horizontal axis, m represents the gradient, and c represents the intercept on the vertical axis.